Soumya, Assistant Professor, Department of Mathematics, School of Computational Sciences, Nehru Arts and Science College, Coimbatore. The overview, learning objectives, correlation, applications, correlation coefficient, summary, and reference. So what are the learning objectives? Understand the concept of correlation, so which is define correlation and explain its significance in statistics. Then differentiate between positive, negative, and zero correlation. So second thing is correlation coefficient interpretation. So calculate and interpret the correlation coefficient, which is represented as R. So understand the range and their meanings. The values lies between -1 and +1. So distinguish between strong, weak, and no correlation based on the coefficient values. So third is correlation versus causation. So understand the difference between the correlation and the causation and recognize that correlation does not imply the causality. So last thing is graphical representation of correlation. So interpret scatter plots to visualize the relationship between two variables. Identify patterns and trends in scalar plots. So this is the correlation. A correlation analysis involves investigating the relationship between two, which means two or more quantitative variables of interest. The goal of such an investigation is typically to estimate or predict the value of one variable based on the observed value of the other variable or variables. So this is the real life applications of the correlation, which is used to estimate for future space flight vehicles like multiple regressions. So and used for predicting when solar maximum will occur, and then estimating seasonal sales for department stores like in the periodic time. So predicting student grades based on time spent for the studying. So this is a correlation. A correlation is a relationship between two variables. The data can be represented by the ordered pairs x, y, where x is the independent or explanatory variable and y is the dependent or responsible variable. A scatter plot can be used to determine whether a linear, which is a straight line, correlation exists between the two variables x and y. So for example, here we have 1, 2, 3, 4, 5 and as an x value and -4, 2, 1, 0, 2 as an y value. So we plot the values and we'll get the straight lines. So these are all the correlation types. So negative correlation, the second one is positive correlation, which rises as x, which is x and y increases. So the third one is a no correlation. There is no correlation if the correlation must lie in the straight line. There is no correlation because the dots are in the other plots. So this is non-linear correlation, which means a straight line which has different ways. So this is the coefficient. The correlation coefficient is a measure of the strength and the direction of a linear relationship between two variables. The symbol Z represents the sample correlation coefficient and the formula for Z is R equal to, so we simply describe as Z or R. So R equal to m into summation xy minus summation x summation y, the whole divided by root of n into summation x square minus summation x the whole square into root of n into summation y square minus summation y the whole square. The range of the correlation coefficient is between -1 to +1. If x and y have a strong positive linear correlation, then R is close to 1. If x and y have a strong negative correlation, the x is close to -1. If there is no correlation or a weak linear correlation, it is close to the value as 0. So this is the strong negative correlation R equal to -0.91. So second one is strong positive correlation R equal to 0.88. So when it is a weak positive correlation, R equal to 0.42, then there is a nonlinear correlation, R equal to 0.07. So for calculating the coefficient correlation, we have the following some of the symbols. For finding sum of the W values, we use ZZ. Finding sum of the J values, we using summation J. Multiply each n value by its corresponding value and find the sum. So square each x value and find the sum, and for also the same for y. So for example, here we have the following data. So we have to find the correlation coefficient for these data. So x is 1, 2, 3, 4 and 5. So summation of x is 15. So y is given as -3, -1, 0, 1 and 2. Summation of y. So adding all those values will get -1. X into y. So multiple x and y will give -3, -2, 0, 4 and 10. The summation value is, overall summation is 9. So squaring the x values, we get the total value as 55, and squaring the y values will get the total value as 15. So here we use the formula n into summation xy minus summation x summation y by n into summation x square minus summation x square into root of n into summation y square minus summation y the whole square. So which gives the value as 0.986, which is a positive, strong positive linear correlation, because the result value is a positive value. Here, another example. The following data represents the number of hours 12 different students watched television during the weekend and the scores of each student who took a test for the following Monday. Display the scatter plot, calculate the correlation coefficient x. So they are giving the values for hours and the test score. So we have to find the correlation coefficient. So we'll plot the values for the given values, scatter plot, and find the correlation coefficient as usual using the same formula xy, x square, y square, and the total values of all those x, y, x into y, x square, y square, and finding all the total values, we'll use the formula r equal to n into summation xy minus summation x summation y by root of n into summation x square minus summation x the whole square into root of n into summation y square minus summation y the whole square. We get the answer as minus, which is negative 0.831. This is a strong negative linear correlation. So as the number of hours spent watching TV increases, the test score tends to decrease. So here, this is the real life example. So this is a testing a population correlation coefficient. How the population can be tested using this correlation coefficient. Once the sample correlation coefficient R has been calculated, we need to determine whether there is enough evidence to decide that the population correlation coefficient is significant at a specified level of significance. One way to determine this is to use the table 11, which we use in the before tables. So if it is a greater than the critical value, it is enough to evidence that the decide that the correlation coefficient is significance. So we have the values for a sample of size n. It is significant at the 5. So its significance level is 0.811. So this is the testing population. Here is the example. The following data represents number of hours for the same question. We are calculating population test. Is the correlation coefficient significance at 0.01? We have to test that. So for r equal to 0 minus 0.831, we'll get the value as 0.708. So which is greater than 0.708, because the population correlation is significant. There is enough evidence at the first level of significance to conclude that there is a significant linear correlation between the number of hours of television watched during the weekend and the scores of each student who took a test the following Monday. So this is the correlation and causation. The fact that two variables are strongly correlated does not in itself imply a cause and effect relationship between the variables. If there is a significant correlation between two variables, then we should consider the following possibilities. Is there a direct cause and effect relationship between the variables? Does X cause Y? No. Is there a reverse cause and effect relationship between the variables? Does Y cause X? It is possible that the relationship between the variables can be caused by the third variable or by a combination of several other variables. It is possible that the relationship between two variables may be a coincidence. So these are all the possibilities we should consider before going to significant the correlation between two variables. So this is the quiz. So what is the range of the correlation coefficient R? It always lies between -1 to +1. If the correlation coefficient between two variables is 0, then it means there is no relationship. So summary. So correlation addresses the questions. Is there a relationship between X and Y? If so, how is it strong? So likewise, the regression address the question, what is the relationship between X and Y? So these are all the references. Thank you.